Okay, so when we look at this curve here, we've established that iron 56 is the most stable of the elements in the periodic table. Let's look at these large elements up here like uranium 235. Okay, because this is less stable, it's got a lower binding energy per nucleon than iron. It's possible for a nuclear reaction to go on here where uranium 235 may make something that's more stable and therefore move up this binding energy per nucleon curve. And indeed that does happen, okay? And there's a number of ways that can happen, but one of the ways it can happen is what we call nuclear fission, okay? So elements like uranium tend to undergo nuclear fission, okay? So that they then produce other elements that have less mass but a higher binding energy per nucleon and are therefore more stable. Okay. Now elements down here have a lower binding energy per nucleon than iron, so they may undergo a process known as nuclear fusion. Okay, so nuclear fission is where an element splits into two smaller nuclei. So the nucleus of uranium-235 may split into two smaller nuclei, and they tend to have then a higher binding energy per nucleon and they're more stable. Nuclear fusion is where you get two lighter nuclei, like helium and hydrogen, for example, that may combine to make a heavier nucleus that has a higher binding energy per nucleon, and that tends to move up the curve towards the peak of stability as a result of that. Okay, so let's look at these heavier elements first, okay, and look at nuclear fission. Okay, so here's an example of nuclear fission. You've got uranium-235 92. That is supposed to be a 5 there. And basically, nuclear fission doesn't normally happen spontaneously. You need to fire a neutron at the nucleus in order to make it unstable enough to undergo nuclear fission and split into two product nuclei or daughter nuclei. Okay, so you've got cesium and rubidium here. So uranium, when you fire a neutron at it, it can split into a variety of different daughter nuclei. And here we've got cesium and rubidium. Now, if we look at the numbers here, on this side we've got 92 and plus 0 for our proton number or our atomic number. 55 plus 37 on this side also makes 92. Okay, so that's okay. 235 is our mass number and 1 for the neutron, so that's 236 on this side. And then 138 and 96 makes 234. So you've got 236 on this side, but only 234 on that side. So what you're going to have as well is another neutron. Well, that will make this up to 235, and it's still 92 on this side because you've got 0 as your atomic number on the neutron. But it's still only 235 on this side and 236 on this side, so you're going to need to have 2 of these neutrons to balance up the equation, okay? Now, what we can then do is look at the masses of these things. Now, remember this is nuclear fission, so we're dealing with nuclei here. So this is uranium nucleus, cesium nucleus, and a rubidium nucleus. Okay, so I've got the nuclear mass of these, not the atomic mass, but the nuclear mass, okay? So it's important to understand the difference. It actually doesn't matter if you use the atomic mass, because all you have to do to work out the nuclear mass is minus the electron mass. But because there's 92 electrons on this side and 92 electrons on that side, it really makes no difference. But I'm going to use the nuclear mass anyway, okay? So the nuclear mass is 234.993415. That's the nuclear mass of uranium, okay, 235. The mass of a neutron is 1.008665 U. So we've got 2 of those here. Mass of cesium is 137.880816 U. Okay. And the mass of rubidium, the nuclear mass of rubidium is 95.913971 U. So what we're going to do is look at the mass of the reactants and the mass of the products. Okay, so if we add up the mass of the reactants, what we get is this. We're going to get 234.993415 plus 1.008665. That's going to give us 236.00208. So 236.00208 U. That's the mass of these two here. Okay, now that then goes to the mass of our products, which is 137.880816. That's the nuclear mass of cesium, plus the nuclear mass of rubidium, okay, plus the mass of 2 neutrons. And that gives us 235.812117. So interestingly here, what you can see is the mass of the reactant is greater than the mass of the products. So when this reaction occurs, uranium splits into these 2 daughter nuclei plus the neutrons. The total mass beforehand is more. The total mass beforehand is more than the total mass afterwards. So what's happened here is some of this mass must have changed into energy. Okay, now we can work out the mass defect here. So the mass defect is going to be equal to that, take away that. So that's going to be 236.00208, take away, so that's going to be 0.189963. Okay, so this much mass, the reactants have this much more mass than the products. So where has that mass gone? Well, what's happened is that missing mass has been converted into energy, and it will be released in the reaction. Okay, so the energy we can calculate now. Okay, so the energy is equal to the mass defect in unified atomic mass units multiplied by 931.5, and that's the energy in mega electron volts. Okay, so let's do that. 0.189963 multiplied by 931.5 is going to give us 176.95053545, and we can round that up then to 176.95, and that's mega electron volts. So that's the amount of energy released. So you're going to get this goes to this plus 176.95 mega electron volts of energy. Okay, so the total mass energy on this side is the same as the total mass energy on this side, because remember we've got not just conservation of energy now, but according to Einstein it's conservation of mass energy. This amount of energy here is equivalent to this amount of mass. Okay, so this mass hasn't just disappeared as the reaction has occurred, this mass has just changed into energy. So if you work out the total mass energy on this side, it's equal to the total mass energy on that side. Okay, so the point is that the mass of the reactants is greater than the mass of the products, and that missing mass, that mass defect, has been converted into energy and is released. Okay, so the total potential energy of the products must be less than the total potential energy of the reactants. These are more strongly bound together on average in their nucleus, and this amount of energy as a result is released. Okay, you can see that this is your uranium. Now your cesium has got a mass of 138, so that's going to be somewhere about here. That's your cesium there, somewhere there. Okay, your rubidium's got a mass of 96, so that's going to be about here. Okay, so what we're saying is this uranium here has split into these 2 things. Okay, these both have a greater binding energy per nucleon than this did. Okay, so so that means that basically these are more stable than this, and that means that they must have released energy. Okay, and that released energy is the energy we just worked out here. That's the amount of energy that's released when uranium becomes these 2 products. Okay, energy is released because these become more stable. Their nucleons are more tightly bound than the nucleons in uranium-235. The nucleons of these in the nucleus of cesium and rubidium are in a lower energy state. They've got less potential energy than the nucleons in uranium-235, and that means that they're more tightly bound. They must have released energy to become more tightly bound. Okay, in the process of losing potential energy, they've released energy. So this is an energetically favourable process for this to split into 2 smaller nuclei, because we've moved up the binding energy per nucleon curve, and that means energy has been released. Now, if you were to try and go from here, if you were to try and join rubidium and cesium to make uranium-235, that would not be energetically favourable, because you would have to put more energy in. You'd have to put energy in to make this happen. Whereas to go from uranium-235 up to cesium and rubidium, nuclear fission, energy is released, so it's energetically favourable. Okay? There you go.